Hello students, I am Professor Suresh Agarwal from Department of Business Economics, South Campus, University of Delhi. Slide 5. After studying this module, you shall be able to know about the term estimation. You would also be able to learn how to conduct interval estimation in linear regression models. Also, we would be able to learn how to identify significance of beta coefficients using interval estimation and to evaluate the individual and group significance of independent variables. In the end, we would learn to analyze the results of testing. So let me introduce the subject to you. Estimation theory is a branch of statistics that deals with estimating the values of parameters based on measured or empirical data that has a random component. The parameters describe an underlying physical setting in such a way that their value affects the distribution of the measured data. In statistics, estimation refers to the process by which one makes inferences about a population based on information obtained from a sample. Let us understand the difference between point estimate versus interval estimate. Statisticians use sample statistic to estimate population parameters. For example, sample means are used to estimate population means, sample proportions to estimate population proportions. An estimate of a population parameter may be expressed in two ways. First, the point estimate. A point estimate of a population parameter is a single value of a statistic. For example, the sample mean X is a point estimate of the population mean mu. Similarly, the sample proportion P is a point estimate of the population proportion P. What is interval estimate? An interval estimate is defined by two numbers between which a population parameter is said to lie. For example, X greater than A but less than B is an interval estimate of the population mean mu. It indicates that the population mean is greater than A but less than B. Confidence intervals. Statisticians use a confidence interval to express the precision and uncertainty associated with a particular sampling method. A confidence interval consists of three parts. First, a confidence level. Second, a statistic. Third, a margin of error. The confidence level basically describes the uncertainty of a sampling method. The statistics and the margin of error defines an interval estimate that describes the precision of the method. The interval estimate of a confidence interval is defined by the sample statistic plus minus margin of error. For example, suppose we compute an interval estimate of a population parameter. We might describe this interval estimate as a 95% confidence interval. This means that if we use the same sampling method to select different samples and compute different interval estimates, the true population parameter would fall within a range defined by the sample statistic plus minus the margin of error 95% of the time. Confidence intervals are preferred to point estimates because confidence intervals indicate number A, the precision of the estimate, and B, the uncertainty of the estimate. What is confidence level? The probability part of a confidence interval is called a confidence level. The confidence level basically describes the likelihood that a particular sampling method will produce a confidence interval that includes the true population parameter. Here is how to interpret a confidence level. Suppose we collect all possible samples from a given population and compute confidence intervals for each sample. Some confidence intervals would include the true population parameters, others would not. A 95% confidence level means that 95% of the intervals contain the true population parameter. A 90% confidence level means that 90% of the intervals contain the population parameter, and so on. Margin of error. In a confidence interval, the range of values above and below the sample statistic is called the margin of error. For example, suppose the local newspaper conducts an election survey and reports that the independent candidate will receive 30% of the vote. The newspaper states that the survey had a 5% margin of error and a confidence level of 95%. These findings result in the following confidence interval, which means we are 95% confident that the independent candidate will receive between 25% and 35% of the vote.
Confidence intervals for regression coefficients beta 1 and beta 2. Instead of relying on the point estimate alone, we may construct an interval around the point estimator, say within 2 or 3 standard errors on either side of the point estimator, such that this interval has, say, 95% probability of including the true parameter value. This is roughly the idea behind interval estimation. To be more specific, assume that we want to find out how close is, say, beta 2 hat to beta 2. For this purpose, we try to find out two positive numbers, delta and alpha, the latter lying between 0 and 1, such that the probability that the random interval beta 2 hat minus delta and beta 2 hat plus delta contains the true beta 2 is 1 minus alpha. Symbolically, this can be written as probability that beta 2 is greater than or equal to beta 2 hat minus delta and is less than or equal to beta 2 hat plus delta is equal to 1 minus alpha. Such an interval, if it exists, is known as a confidence interval, and 1 minus alpha is known as the confidence coefficient, and alpha, which is between 0 and 1, is known as the level of significance. The endpoints of the confidence interval are known as confidence limits, also known as critical values. Beta 2 hat minus delta being the lower confidence limit and beta 2 hat plus delta the upper confidence limit. In a passing, note that in practice, alpha and 1 minus alpha are often expressed in percentage forms as 100 alpha and 100 into 1 minus alpha percent. An interval estimator, in contrast to a point estimator, is an interval constructed in such a manner that it has a specified probability 1 minus alpha of including within its limit the true value of the parameter. Slide 9. If alpha is equal to 0.05 or 5%, we would read the probability that the random interval shown there includes the true beta 2 is 0.95 or 95%. The interval estimator thus gives a range of values within which the true beta 2 may lie. If alpha is equal to 0.05 or 5%, we would read the probability that the random interval shown there includes the true beta 2 is 0.95 or 95%. The interval estimator thus gives a range of values within which the true beta 2 may lie. Recall that in our regression model, we are stating that expected value of y given x is equal to beta 0 plus beta 1 x. In this model, beta 1 represents the change in the mean of our response variable y as the predictor variable x increases by 1 unit. Note that if beta 1 equal to 0, we have that expected value of y given x is equal to beta 0 plus beta 1 x, which is equal to beta 0 plus 0 into x, and hence is equal to beta 0, which implies the mean of our response variable is same at all values of x. In the context of the coffee sales example below, this would imply that the mean sales are the same regardless of the amount of shelf space. So a marketer has no reason to purchase extra shelf space. This is like saying that knowing the level of the predictor variable does not help us predict the response variable. Under the assumptions stated previously, namely that y is distributed normally with mean beta 0 plus beta 1 x and variance sigma square, our estimator beta b1 has a sampling distribution that is normal with mean beta 1, which is nothing but the true value of the parameter, and standard error defined as sigma divided by under root of sigma xi minus x bar square, where summation is over 1 to n. That is, B1 we can say is normally distributed with beta 1 as mean and variance as sigma by SSXX, where SSXX is sum of the squares of x from x only. First, we now obtain the standard error of B1, which is estimated. Now, this is the standard deviation of its sampling distribution. We can write this as SB1 equal to standard error of E, SE, divided by under root of SSXX, which is equal to SE upon under root of n minus 1 SX square. The interval then can be written as B1 plus minus T alpha by 2 n minus 2 into SB1. This is equal to B1 plus minus T with the alpha by 2 and n minus 2 degrees of freedom into standard error divided by the sum of the squares under root, which is under root SSXX. Please note that SE upon under root SSXX is the estimated standard error of B1, since we use standard error equal to under root of MSE, which is mean square error, to estimate sigma. Also, we have n minus 2 degrees of freedom instead of n minus 1, since the estimate SE has two estimated parameters used in it. Let's take some examples. For the coffee sales example, we have the following results. Suppose B1 is equal to 34.5833, SSXX is 72, and SE is equal to 51.63 with n equal to 12. So a 95% confidence interval for the parameter beta 1 can be written as 34.5833 plus minus t 0.025, 12 minus 2 into 51.63 divided by under root of 72. On simplification, this is equal to 34.5833 plus minus 2.228 into 6.085. And again, on simplification, we get this equal to 34.583 plus minus 13.557, which gives us the range of 21.026 and 48.140. We are 95% confident that the true mean sales increase by between 21.026 and 48.140 bags of coffee per week for each extra foot of shelf space the brand gets within the range of 3 to 9 feet. Please note that the entire interval is positive, which means basically it is above 0. So we are confident that in fact beta 1 is greater than 0. So the marketeer is justifying or is justified in pursuing extra shelf space. We have another example of Hosiery Mill's cost function. Suppose similarly we have B1 equal to 2.0055 and SSXX is 7738.94 and SE is equal to 6.24 and N is equal to 48. We can similarly substitute all these values and we can find out that the confidence interval comes out to be 2.0055 plus minus T 0.025 with degrees of freedom 46 into 6.24 divided by under root of 7738.94. Now this is equal to 2.0055 plus minus 2.015 into 0.0709. And on simplification, we get this equal to 2.0055 plus minus 0.1429. And this gives us the confidence interval of 1.8626 and 2.1484. So we can say that we are 95% confident that the true average unit variable costs are between $1.86 and $2.15. This is the incremental cost of increasing production by 1 unit, assuming that the production process is in place. So similarly, we can define it for coefficient beta 2 as we have done it now in the present case for beta 1, and it was estimated by B1. Confidence interval for sigma square. We know that test for chi square can be written as chi square equal to n minus 2 into sigma hat square divided by sigma square. This is our equation 1. Now this follows the chi-square distribution with n minus 2 degrees of freedom. Therefore, we can use the chi-square distribution to establish a confidence interval for sigma square. How do we do it? Now this can be written as probability of chi-square into with 1 minus alpha by 2 as the confidence limit, which is less than or equal to chi square, which is less than or equal to chi square with alpha by 2. Now this probability is equal to 1 minus alpha. This is our equation 2. So let me repeat here that we are saying that this interval could be written as probability of chi square lying between chi square 1 minus alpha by 2 and chi square alpha by 2 is equal to 1 minus alpha. So in this, the chi-square value in the middle of this double inequality is as given by the equation 1. And our chi-square 1 minus alpha by 2 and chi-square alpha by 2 are two values of chi-square which are also the critical chi-square values and are obtained from the chi-square table for n minus 2 degrees of freedom in such a manner that they cut off 100 into alpha by 2 percentile areas of the chi-square distribution. Now substituting chi-square from 1 into 2 and rearranging the terms, we obtain which gives the 100 into 1 minus alpha percent confidence interval for sigma square. The interpretation of this interval is that if we establish 95% confidence limits on sigma square, and if we maintain a priori that these limits will include true sigma square, we shall be right in the long run 95% of the time, which means out of 100 samples, 95% samples will have this value of chi square within this confidence interval. confidence sets for multiple coefficients. Let's have yi equal to beta 0 plus beta 1 x1i plus beta 2 x2i, so on up to beta k xki plus ui, where I takes the values from 1 to n. For the above regression model, a joint confidence set for beta 1 and beta 2, that is 95% joint confidence set, is a set valued function of the data that contains the true parameters in 95% of hypothetically repeated samples. The set of parameter values cannot be rejected at 5% significance level. We can find a 95% confidence set as the set of beta 1, beta 2 that cannot be rejected at the 5% level using an F test. So let F with beta 1 0 and beta 2 0 be the heteroscedasticity robust F statistic testing the hypothesis that beta 1 is equal to beta 1 0 and beta 2 is equal to beta 2 0. For this, the 95% confidence set can be written as the beta 1 0 and beta 2 0 such that the F beta 1 0 of beta 2 0 is less than 3. Here 3 is the 5% critical value of F2, infinity distribution. Now this set has coverage rate 95% because the test on which it is based, that is the test it inverts, has size of 5%. That is 5% of the time the test incorrectly rejects the null when the null is true. So 95% of the time it does not. Therefore, the confidence set construed as the non-rejected values contain the true value 95% of the time, which means in 95% of all samples. So the confidence set based on F statistics is an ellipse in this case, and we have the formula, you can see it on your screen, for this ellipse. Now this shows that it is a quadratic form in beta 1 0 and beta 2 0. Thus the boundary of the set F equal to 3 is an ellipse. Now suppose we have below regression showing consumption expenditure Y corresponding to level of income X, such that yi hat is equal to 24.4545 plus 0.5091 xi, where yi hat is the estimator of true expected value of yi corresponding to given x. What use can be made of this historical regression? Now, one use is to predict or forecast the future consumption expenditure Y corresponding to some given level of income X. Now, there are two kinds of predictions. One, which is prediction of the conditional mean value of Y corresponding to a chosen X, say X0, that is the point on the population regression line itself. And second could be the prediction of an individual Y value corresponding to X0. We shall call these two predictions the mean prediction and individual prediction. Mean prediction. To fix the ideas, assume that X0 is equal to 100 and we want to predict expected value of Y given X0 equal to 100. Now it can be shown that the historical regression above provides the point estimate of this mean production as follows. We know that y0 hat is equal to beta 1 hat plus beta 2 hat into x0, where we have substituted the value of x0 and we get the value of y0 hat. Now on substitution, we get this equal to 24.4545 plus 0.5091 into 100. and on simplification this is equal to 75.3645, where y0 hat is estimator of expected value of y given x0. Now it can be proved that this point predictor is a best linear unbiased, or known as blue. Now since y0 hat is an estimator, it is likely to be different from its true value. The difference between the two values will give some idea about the prediction or forecast error. To assess this error, we need to find out the sampling distribution of y0 hat. Y0 hat is normally distributed with mean beta 1 plus beta 2 x0, and the variance is given by the following formula, which is that variance of y0 hat is equal to sigma square into the bracket 1 upon n plus x0 minus x bar whole square divided by sigma xi square, bracket closed. By replacing the unknown sigma square by its unbiased estimator sigma hat square, we see that the variable follows the t-distribution with n-2 degrees of freedom. The t-distribution can therefore be used to derive confidence intervals for the value or for the true expected value of y0 given x0, and the test hypothesis about it in the usual manner. Namely, we can write this as probability that beta 1 plus beta 2 x0 is greater than or equal to beta 1 hat plus beta 2 hat x0 minus t alpha by 2 into standard error of y0 hat, but is less than or equal to beta 1 hat plus beta 2 hat x0 plus t alpha by 2 into standard error of y0 hat. This probability is equal to 1 minus alpha. On substituting the values in the above equation, we get variance of y0 hat equal to 42.159 in the bracket 1 by 10 plus 100 minus 170 whole square divided by 33,000, and this comes out to be on simplification equal to 10.4759. Now we can see that therefore standard error of y0 hat is equal to 3.2366. Therefore, the 95% confidence interval for true expected value of y given x equal to x0 is equal to beta 1 plus beta 2 x0, and is given by the values which we may substitute, which are 75.3645 minus 2.306 into 3.2366 less than or equal to expected value of y0 given x equal to x100, which is less than or equal to the 75.3645 plus 2.306 into 3.2366. So that gives us the interval of 67.9010 and 82.8381. Thus, given x0 equal to 100, in repeated sampling, 95 out of 100 intervals will include the true mean value. The single best estimate of the true mean value is, of course, the point estimate 75.3645. Individual prediction. If our interest lies in predicting an individual y value y0 corresponding to a given x value, say x0, then a best linear unbiased estimator of y0 is also given as in first equation under this topic, but its variance is as follows, which means variance of y0 minus y0 hat is equal to expected value of y0 minus y0 hat, and this on simplification comes out to be equal to sigma square into 1 plus 1 by n plus x0 minus x bar square divided by sigma xi square. Let me clarify, the x in the numerators are capital X, whereas the x in the denominator is small x, which is the deviation of x from the mean. Now it can be shown further that y0 also follows the normal distribution with mean and variance given by our above formulas respectively. Substituting sigma hat square for the unknown sigma square, it follows that t now is equal to y0 minus y0 hat upon a standard error of y0 minus y0 hat. And this also follows the t distribution. Therefore, the t distribution can be used to draw inferences about the true y0. Continuing with our consumption income example, we see that the point prediction of y0 is 75.3645, the same as that of y0 hat, and its variance is equal to 52.6349. Therefore, the 95% confidence interval for y0 corresponding to x0 equal to 100 is seen to be y0 given x0 equal to 100 is greater than or equal to 58.6345 but is less than or equal to 92.0945.
Estimation and hypothesis testing constitute the two main branches of classical statistics. Preceding question, confidence interval and test of significance. Underlying the confidence interval approach is the concept of interval estimation. An interval estimator is an interval or range constructed in such a manner that it has a specified probability of including within its limits the true value of the unknown parameter. The interval thus constructed is known as a confidence interval, which is often stated in percent form such as 95 or 90%. The confidence interval provides a set of plausible hypotheses about the value of the unknown parameter. If the null hypothesis or null hypothesized value lies in the confidence interval, the hypothesis is not rejected, whereas if it lies outside this interval, the null hypothesis can be rejected. Thank you.